Thank you very much. Good morning, everybody. So today is kernel day, or at least the morning is kernel morning. I guess many of you know about kernels, so can I get a quick show of hands who has ever trained an SVM? Okay, that's more than half. Who has used another kernel algorithm? Who knows what a kernel is? That's a lot. Who knows how to construct the reproducing kernel Hilbert space for a given kernel? Okay, that's a lot less. That's good, because that's what I'm planning to do today. So hopefully you'll learn something new, and then at the end we'll have a bit of fun with a kernel quiz. So I shouldn't lose too much time. I want to get to the quiz at the end. And so just a little bit of background. So normally I teach statistical learning theory before kernels, but this time we have someone much better teaching statistical learning theory, because Ingo Steinwart is going to come next week. So I'm not going to bore you with this, and I'll just start directly with kernels. But as a little bit of background, so learning theory, I mentioned already in my introduction, was started by Wapnick-Jawoninkis in the 60s, and just very roughly speaking is, the model is that we observe data that's generated from an unknown regularity. The regularity is modeled by a probability measure of some random variables, a joint measure of x and y, and we sample IID from this regularity. We don't know the regularity, so it's not just a matter of making predictions from it, but actually inferring it. That's what we call learning. And the crucial thing in learning theory is that Wapnick-Jawoninkis, they were studying this thing called empirical risk minimization. So trying to choose models based on how well they do on the training data, so just training error minimization. And they were studying under which conditions this process is consistent, which means that if you are given infinitely many data points, will you converge to the best possible solution, or to a best possible solution? And it turns out that's highly non-trivial, and that only works if one takes into account certain properties of the function classes that the learning machine can implement. In a certain sense, it only works if the function classes have a limited capacity or complexity. And then the question is how to compute this complexity capacity, and they came up with some things like the VC dimension. So this is really quite a profound analysis of learning and generalization. So it turns out one has to control these capacity measures, and then the question is, in practice, how do we do it? We need, on the one hand, we need function classes that are, in some sense, simple enough that we can even just compute the capacity measures, because they are complicated combinatorial quantities. On the other hand, the function classes are supposed to be sufficiently rich or non-linear that we can do something useful with them. And there's this beautiful trick that sort of satisfies both at the same time, so mathematically simple, but nevertheless non-linear and complex, and that involves kernels. Okay. Yeah, and then one more specific thing, one class of classifiers for which these capacity measures, or the VC dimension, has been computed, or at least bounded, is the class of so-called separating hyperplanes. So support vector machines are built on this, and it turns out that for separating hyperplanes, there's two ways of controlling the capacity. One is there's a bound just in terms of the dimensionality of the space. So in that case, the complexity is essentially the dimensionality. That's bad if we want to work in a high-dimensional space. But there's a second way of bounding the complexity of separating hyperplanes, and that depends on the margin of separation that these hyperplanes induce. So if it turns out that a hyperplane induces a large margin of separation between the positive and negative class, so let's assume we're talking about binary classification, then we can give a bound that depends on this margin of separation and not explicitly on the dimensionality of the space. So it turns out if we have a large margin of separation, we can have a small VC dimension even in an infinite dimensional space. So now the message is we want to construct nice function classes. We're not scared of infinite dimensionality, but we want the theory to be simple, and we want them to be such that we can implement them in algorithms. So that's a starting point. So what the basic idea is, we pre-process the data with a mapping phi that takes our input domain, and for the input domain we don't make any assumptions right now other than that it's a non-empty set. We pre-process the data by mapping the input domain into a dot product space, so a vector space with a dot product. So each point gets mapped into an element of this space. And then we try to solve our learning problem based on this kind of data rather than on this kind of data. So when this, usually in these settings, the dimensionality of H is very large and much larger than the dimensionality of this, if this has a dimensionality at all. As I mentioned, it could just be a set. And that was a bit of a shock when SVMs were introduced, because statisticians especially didn't like that. They thought you're blowing up the dimensionality of the data, but you're not creating additional data, so you're just making the problem harder. But as I just mentioned, from the point of view of VC theory, the crucial issue is the capacity or complexity of a function class, which sometimes coincides with the dimensionality, but not in general. Okay, so there's a simple example, which is using polynomial features of order 2. So in this example, we have a two-class classification problem. So we want to separate these red circles from the blue crosses. And we want to do this the following way. We first map the training points, so these are our training points, into a three-dimensional space that is spanned by all monomials of degree 3. And then we are going to do a very simple kind of separation in that space, a hyperplane separation. And if you think about it for a second, if you work in these coordinates, this ellipse here, which is the underlying optimal but unknown decision boundary, when written in these coordinates, it just becomes an affine equation. So it's just a separating hyperplane in these coordinates. And actually, it's even for this axis-aligned ellipsoid, it's a hyperplane that doesn't even depend on the second coordinate. On this, it doesn't have a mixed term here. So in this space, if we were to blow up the dimensionality, of course, in this case, only from 2 to 3, and computer separating hyperplane in this space, it would be very simple to separate these data. Now, suppose we wanted to do the same thing with n-dimensional inputs and features of order D. In that case, we would have to map into a space whose dimensionality grows to n to the power of D. I still have these very old pictures. That's the kind of data that people used to work on in machine learning. But already for this kind of trivial data, the dimensionality would be 10 to the power of 10. And that's where this trick comes in. I'll show you the trick first for the three-dimensional case. If we take 2 points, x and x prime, map them into the three-dimensional space, and then compute a dot product, we actually get a complete binomial formula, which we can write as the square of this dot product. I think you can probably verify this on a piece of paper, or you just believe it directly. So that's very easy. And then we interpret this as a kernel. By this, so far, I only mean it's a function of x and x prime. It's actually a function that can be evaluated very easily, and a function that, if we're only interested in dot product, allows us to not carry out this mapping into the high-dimensional space. We just compute directly this function here, and then we know how to compute dot products in that space. And we can do the same thing in the n-dimensional setting, and we'll just start with the same kind of formula. So let's try to take 2 n-dimensional vectors, compute the Euclidean dot product, and raise things to the power of D. Let's see what that gives us. So this is the dot product. We raise it to the power of D. That gives us D sums here. I've called the indices J1 through JD. And then back there, we get all these terms, and we can sort them if we want, such that everything involving x comes first and everything involving x prime comes second. And if you then look at this thing, so this is a big sum over n to the power of D terms. This is a function of x. This is the same function of x prime. So we can interpret this sum as a dot product in an n to the power of D dimensional space. So let's write a dot product, and let's call this a function of phi. It's the same function here, just evaluated at x prime. So this is a dot product after some mapping phi, and we can actually read off what the mapping phi does. It just computes all possible products of input coordinates, of D input coordinates of our input vectors. So all possible monomials of degree D. So in this case, these are ordered monomials. We don't care about the ordering. If we could take unordered ones, and then we would get some correction factors similar to this square root of 2 here. But let's not think about that now. Okay. So this is maybe the first kind of kernel that people thought of using in the context of SVMs. But It was noticed fast that one can use other kernels, and in the first years of kernel research, people usually refer to Mercer Theorem as the reason for this. This is the theorem that tells us how one can diagonalize kernels of positive definite integral operators. If you don't know integral operators, don't worry, you don't have to understand this. I just want to show you, because sometimes people call these kernels Mercer kernels. So if we have this kind of positivity condition, then it turns out that the kernel can be expanded in such an infinite sum where these eigenvalues are non-negative. And if we have such an expansion, then we can, from the expansion, construct a feature mapping that satisfies this equation here, that the kernel corresponds the dot product after the feature mapping. So this is just one way to construct such a feature space, but of course you can only do that if you believe Mercer's theorem. So we will do something more elementary and more general in maybe 5 or 10 minutes. Okay, so any questions after here? You just interrupt me at any point.
On the previous slide, it was just positive definite or some more conditions?
Or some more.
Conditions on the kernel.
So the question is it just positive definite, or are there more conditions? So here there's also the condition that it's continuous and that X is a compact space. These are technical conditions in the original Mercer theorem. One can slightly I think actually the original Mercer theorem even is just for the one-dimensional case. So this is already a slightly generalized version, but we will get rid of these conditions later on. So that's why I didn't stress them right now. But so right now let's assume it's don't worry too much about it. So the Mercer theorem has some conditions, but we don't have to worry about them because they're not really necessary. We will get rid of them later on. Yeah. Okay. So now the real definition. So that's what people notice later on. Actually, this is the class of kernel that one can use. And it contains Mercer as a special case. So these are called positive definite kernels. And we'll go more slowly with these, and also I'll make you try out some things yourself and so on. So let's assume X, as before, is a non-empty set. And let's consider functions that take two elements of X as an input and produce a real number. We can also do it for complex, but let's not worry about this now. Then there are two equivalent statements. One is that K is positive definite. I'll tell you in a second what that means. And the second statement is there exists a map into some dot product space. So there exists a dot product space and a map, I should say, into this space, such that the kernel is equal to the dot product evaluated in that space. So there's two things. So there's this class of kernels called positive definite. There's this class of kernels that can be written as dot products in another space, and these classes are actually the same. So whenever I have a positive definite kernel, I can construct a dot product space and affirm that this is true. And whenever I have such a mapping, and from this mapping I define a kernel function like this, then I can prove that this kernel is actually positive definite. Okay, so this is nice. We'll spend some time on this. This tells us whenever we pick a kernel that satisfies this condition, then we can actually think of this kernel as a dot product somewhere else, which means that it's much easier to analyze theoretically. We can do things like compute VC dimensions, etc. But it's also nice from the algorithmic point of view, because whenever we have an algorithm that only depends on dot products, we can then say, well, actually, let's carry out this algorithm in this space H, and we're not worried about its dimensionality. It might be even infinite dimensional, because if our algorithm only needs dot products, we will do everything in terms of these kernels. Okay. This space is called a reproducing kernel Hilbert space. I'll get to this. I should say one more thing. So in my definition here, this is called positive definite. Some people would call this positive semi-definite. So it depends on the exact community. I think in approximation theory, they call it positive definite. Doesn't matter, so that's just our definition. There's a slightly stronger condition, which we then call strictly positive definite. And that stronger positions condition says that, so clearly, if these AI are 0, all of them, then this sum will be 0. How about the other direction? So if the sum is 0, does that imply that the AIs are 0? So if that's the case, if this implication is true, then we call it strictly positive definite. And I should have said this is for pairwise distinct points. So if you end up having a set of training points where two identical points, so where there's a point that appears twice, then you will always have a situation where this quantity can be 0, even though A is not 0. But if all training points are distinct, then it's possible that this is strictly true in this sense down here, so that this is an if and only if. This is 0 if and only if the vector A is 0. In that case, we call it strictly positive definite. So that's a slightly stronger condition. It's a bit like if you talk about a matrix, it can be positive semi-definite or positive definite. It's the same kind of relationship. So for instance, a strictly positive definite kernel will have a kernel matrix. So that's the kernel matrix. You take this kernel, you have a training set. Now you substitute all possible training points in here. You get an M by M matrix. For a positive definite kernel, this M by M matrix has non-negative eigenvalues. So it's a positive definite matrix. And for a strictly positive definite kernel, this matrix will have strictly positive eigenvalues. So it's a strictly positive definite matrix, or whatever terminology you want to use. But just for the next 2 hours, let's call this strictly positive definite. Okay. Yeah, so I've already discussed this a little bit. So if we have an algorithm that only depends on dot products, we can kernelize it. So kernelizing means you write the algorithm such that the data only appears through dot products. So no data point is there alone. Every data point is paired with another one in the dot product. If that's the case, we can substitute kernels for dot products. So that's what people mean when they say they kernelize an algorithm. And a lot of algorithms have been kernelized in the last 10 years. So that's nice. Maybe even more significant than this is that we can this way, using the kernel trick, so as I mentioned, the kernel doesn't require that this input domain is a vector space. It's just could be any non-empty set. So therefore, a significant aspect is that if we can define a kernel on this kind of data, it could be strings or trees or whatever you like. If we can define a positive definite kernel on that data, we get a vector space representation for free. So we get this. We know that even though these things are strange objects, there's a mapping into a vector space with a dot product. That's as nice as it gets in mathematics, where this is actually a dot product. So we get this representation in a vector space. So we can we start with non-vectorial data, and we can still handle them as if they are vectors. That's nice. One way to think of the kernel is it's some kind of nonlinear similarity measure. I've already mentioned polynomial. This is a so-called inhomogeneous polynomial. If we have some positive constant in here, there's the Gaussian kernel, and this has been already mentioned, I think, by Chris or Zubin. Kernels are also used in Gaussian processes, for instance, as covariance functions. So that's the same class of objects, essentially. Although one should say that in the Gaussian process community, it's not very common that people use kernels defined on non-vectorial data. Okay, so let's look at some properties. And now, so this is the abstract definition of positive definite kernels. To get used to it, it's good to play with it a little bit. So I'll give you a bit of time to prove some things about kernels, but maybe not those. Let's see. Maybe we'll do it a bit. Let me think which ones. Yeah, maybe not those. So the next ones. Okay, so well, let's do the first one, but not the second one. Yeah. Okay, so please take a piece of paper, and first write down this definition here, because I can't show both slides at the same time. Or maybe I can write it on here. Wait. Okay, so that's the positive definite kernel. And so here's the statements that we want to prove. Let's prove the first one. So we want to prove that this is positive definite. And actually, let's do all at the same time, because then you can think about several problems and we solve them jointly at the end. So the second one is k of x is non-negative for all x. And then we have this one, nice one. Right. Okay, so so I'll give you 5 minutes, and maybe you can take a piece of paper, talk to your neighbor, discuss, think about it, play around with the definition bit, and then we'll do it together. And I'll try to remember meanwhile how it goes. So can I briefly ask who has solved one or more problems? Okay, who has solved two or more? Three or more? Okay, and the ones who haven't solved, so maybe I'll give you another 2 minutes and then we'll do them, okay? Say the easiest one maybe is the first one, or the second one is also relatively easy. The third one is a little bit harder. And to solve the first one, you have to substitute this definition. You have to substitute this kernel, or this hypothetical kernel, into this definition and check that the definition holds true. So. So can I ask again? Who has solved the first problem? Okay, and of the ones who have not solved the first problem, who has not yet tried to substitute this into this equation? You can answer truthfully. I'm not going to drag anyone to the blackboard against their wishes. In fact, I think I'm not going to drag anyone. I'll just do it and you help me do it. Okay, so everybody has tried substituting it, but might not be finished yet. So I'll give you another minute and then we'll do it. Oops. Let's do the first one, okay? So any ideas, any recommendations? Well, I already said the recommendation, I guess. So maybe the first one I'll just do, but then the second one I'm going to ask recommendations. So we want to, this is now our object, which we want to prove is positive definite. How do we do that? We have to check that this condition is true here. So let's substitute it. So we have AI aj, and now we substitute the kernel, which means phi of xi, phi of xj. Okay, so now we have to use some property of dot products. Any idea what we should use? Something nice that dot product satisfies. So you can just call it out and I'll do it. Linearity, good. So linearity means two things, that we can move these scalar factors in and out, and we can move sums in and out. Okay, let's move both in and out. And in fact, so we have one sum over I and an AI. We have a sum over j and an aj. So of course, everything that involves I fits better in here. Everything that involves j fits better in here. Okay, let's do that. Okay. Notice I also have this Darth Vader breathing today. Yeah, I think I walked, I came here too fast. That's why I was a little bit late. I was, so Leon and Marina, Leon, one of our speakers, just arrived and they came from the airport and I wanted to see them before I ran off from my house. Okay, so now this is true due to linearity. Now if we look at these things, these two things are actually the same, right? Because J is just an index, we sum over it. So this is the same quantity, let's call it V. So this is some vector V with itself, and now we have to use second product of property of dot products, which is called positive definiteness. So a vector with itself always gives us a non-negative number, and we're done. Okay? Any questions? So that's the first. That's the first part, and actually that's nice because of this statement that we were talking about before. So we had this statement here that the positive definite kernels. So a kernel is positive definite if and only if has this feature mapping. So we have now proved half of this, right? We have proved one direction. We have proved if there's such a feature mapping, then it's positive definite. Okay, and the rest of the next 20 minutes or 15 minutes will be the other direction. If it's positive definite, then there's a feature mapping. Okay, so we have proved the first direction. That's good. And now this one I'll leave as an exercise if you want. You can try this one yourself. This is, yeah, just try this. Right. If you use this trick, this is very easy. But now we move to this thing here. So it's written here. So that was one. Okay, so any suggestions how to prove number two? Yes. Okay, so this thing here is a squared k of x comma x. That's so what we want to prove is, yes, okay, yeah. So we know that this thing here, we know that this is a kernel, so we know that this is non-negative, okay. Okay. How about if a is 0? Is that a problem? It's not a problem because we can choose it, right? We can choose any a. We can even choose a equals 1 if we want to, and then, yeah. So you're right. That's correct. Let's make it even easier. We just choose a equals 1, substitute it in here, choose m equals 1. We have only 1 point. Then that's what we wanted to prove, actually. Yes. So you want to use that k of x is equal to phi of x with itself. So if you know that already, you can use that. But ideally, we would like to prove this, right? Because there's these two directions. So k is, let's wait. So the definition is the red thing. But it turns out it's a theorem that is equivalent to the blue thing. And we have already shown that the blue thing implies the red thing. And now we want to show that the red thing implies the blue thing. So strictly speaking, we should not yet use it. We prove it step by step, but it's correct. Yeah. Well, in the first one, well, the assumption was so the first one, the assumption was there exists a mapping phi and a dot product. We define this thing, and now we want to prove that it's positive definite. In the second one, the assumption was it's positive definite. Wait, let's see. Maybe I hope it's written properly here. So in the first one, we don't assume that it's positive definite. We just assume that it's defined like this. We prove it's positive definite. In the second ones, we assume positive definiteness, and then we prove certain properties. So I didn't make this perfectly clear, but it's good that you asked. So yeah, so it's they concern different directions. Yeah. Okay. Yes. Okay, let's do the last one. Yeah, yeah. So the thing is, if the kernel is positive definite, so our definition is that all this is true. So it's true for all m. So we are allowed to. So in particular, it's true for m equals 1. And if that's enough to complete our proof, we're fine. Right? We're allowed to use any part of this. Okay. Okay, so let's do the last one, unless there are more questions about the second one. Okay, so the last one. So this is the slightly tricky one, and maybe also notice that this is a generalization of the Cauchy-Schwarz inequality. So the Cauchy-Schwarz inequality, if k were just a dot product, then the Cauchy-Schwarz inequality gives us an upper bound on the dot product between x and x prime in terms of the squared length of x and the squared length of x prime. So this is a generalization. And the dot product, so do people know the Cauchy-Schwarz inequality? Or who does not know the Cauchy-Schwarz inequality? Okay, okay. So the Cauchy-Schwarz inequality says if we have a dot product, I think one can write it in different ways, but I think normally it's written like this. But we can also square it. So if we square this thing, we get something like this. Now this is the same as x, and this is x prime with x prime. Okay, so this is the Cauchy-Schwarz inequality. So you can see formally it's the same. And this Cauchy-Schwarz inequality just tells us the dot product, the maximum value that you can get is the length of the one vector times the length of the other one. And actually that only happens if they're aligned or anti-aligned. Okay, so this is in this sense, and also a normal dot product is a special case of a kernel. So it makes sense that this is called Cauchy-Schwarz inequality. It's a real generalization. So let's prove this one. So are there any ideas how to do it? Or has it? Okay.
Well, actually, it says you compute the determinant of the Gram matrix of your x and your x squared. So because of the property, you actually know that this 2 by 2 matrix is positive definite as a matrix, hence the determinant is positive.
Yeah.
Then you just compute the
Okay. Let's do that. That's correct. Yeah. So let's look at this Gram matrix. So here this was the special case for m equals 1. Now let's look at the special case for m equals 2. So let's take 2 points. We're allowed to use just 2 points. It's a special case. It's implied by this. Let's call them x and x prime, and then we compute this kernel matrix. And the kernel matrix will be this one. Okay. Now we compute the dot product, or maybe we should, the determinant, but what we do first is we use the symmetry. So here in the definition, actually I didn't write this here, it's written up here. So in the right definition, K is symmetric. I forgot to put that here. So maybe some of you failed because I didn't write that here on the blackboard. Maybe for the experts, a little subtlety here. So in this case of a real valued positive definite kernel, we have to require this as a condition. So that's why I wrote it up here in red. It turns out if in the complex case we don't need this, because in a sense in the complex case this this condition is stronger. That this is always true for all complex coefficients also, and then the condition actually implies that K is symmetric. But in the real case we have to require it, so let's add it here. Let's use it here. So this equal thing is equal to this. So let's actually write it like this. Okay, and now we compute the determinant. So determinant of a 2 by 2 matrix is this times this minus this times this. I should remove this. Okay, so this times this minus this times this, which is the same. So we just get the square. Okay, and also you said we know it's a positive definite, this matrix, because essentially this is also the definition of positive definiteness for matrices. Therefore, the matrix has a determinant that's non-negative. So one can either just know this, or you can remember the determinant of a symmetric matrix is just the product of its eigenvalues. And the eigenvalues of a positive definite matrix are non-negative. So it's the product of two non-negative numbers. Therefore, it's non-negative itself. So we know it's non-negative. So we know that this is smaller than this. And now let's just add this on both sides. So then we have this quantity over here. And on the other side, we're left with this. Okay. And this is, hopefully, yes, this is what we wanted to prove. Okay, any questions about this? Yes.
Did you also use the phi and then use the Cauchy-Schwarz only?
Well, if you already know that you have a phi that corresponds to this k, then you can do that. But we would like to use this to prove that there exists such a phi. Yeah. So, but once you know this, a lot of these proofs become much more elegant by using the phi. So, actually, if you know that something is a positive definite kernel, and if you know this this equivalence, which in practice you do know. Wait, where is it? If you know this equivalence between the red and the blue thing, then most of the things you will prove just using the feature mapping phi. So that's the most elegant way of doing things usually. Yeah. Yeah. Okay. Okay, so then here we have another statement that's kind of interesting. So I'm claiming that, so this thing here is sometimes called positivity on the diagonal, right? Because x prime, if you think of the matrix elements, these are these values will be the diagonal elements of the matrix. Now it turns out this statement says that if the diagonal is 0, for all x, no matter what you put in, then actually the kernel is 0 everywhere. Okay, so this, which kind of makes sense, because this equation tells you that the general elements of the kernel matrix are somehow upper bounded by what's going on the diagonal. And in particular, of course, if this thing here is equal to 0 everywhere, that means the right-hand side here is always 0. So we have an upper bound on this quantity, which is a non-negative number, and the upper bound is 0. Therefore, in this case, this number is always 0. Okay? So if the diagonal is 0, the kernel is 0 everywhere. And let's look at a few more properties. So it's if you want, it's a nice exercise to play with the definition, but these ones we will not prove here. If you multiply a kernel with some non-negative number, you get a kernel. In particular, you can multiply it by 0, so the 0 is also a kernel. If you sum two positive definite kernels, so I'm assuming all these things are positive definite, if you sum two positive definite kernels, you get a positive definite kernel. If you take the limit of a sequence of positive definite kernels, you get one if it exists. This one is less trivial, and maybe for the very smart ones, you can try to prove this. Once at a summer school in France, I had someone who managed to prove this elementarily, not during the lecture, but afterwards. So this is it's non-trivial. It's a theorem of Schur. That if you take two positive definite kernels, take the pointwise product, it's also positive definite. So that's interesting. It also means that if you have two if you have two positive definite matrices and you take the pointwise product, so positive definite matrices of the same size, you take the pointwise product, you get a positive definite matrix. And there are other things that one can do. Okay, so you just stop me whenever you want. Now let's construct the feature space. Okay, so we assume we know the kernel is positive definite, and now we will constructively show that we can think of it as a dot product in another space. And the way we'll do it is first we have to define our feature map, and we will say the following. The feature map takes as input some point x from our input domain, and it maps it into a function that we get by placing a kernel on that point x and thinking of it as a function of this first open argument. So for instance, if we have a Gaussian kernel, that means we have a point x. This mapping takes this point x to a Gaussian that's centered on x. And it takes this point x prime to a Gaussian centered on x prime. So now we are in the space of functions, so that's just a shorthand for saying these are functions from x to r. Okay, and then now we have to tell you why is this sensible, or why can we do things such that this equality here will hold true. So far I've only told you what the mapping does. I haven't given any structure to this space. In particular, there's no dot product yet. And whether this equation here holds true, of course, will depend on how we define the dot product. So let's see. Okay. So the first thing is first to just make it a vector space, because I said it's a dot product space. So in particular, it's a linear space, vector space. How do we make it a vector space? Well, we just formally say, so far we know that our space has elements of this form. Right? These are the images of points in the original space. But I'll just say, if we take linear combinations of such elements, they're also supposed to belong to our space. Okay, so we just formally say we take the linear hull of all such elements. We can do that. So then we get functions like this one or like this one. And I need two because I want to define a dot product. So I will write a generic function f in terms of expansion coefficients alpha I and expansion points xi. So that means f will be a sum of such Gaussian bumps sitting in different places with different weights on them. That's my function f. It's an element of this function space. And the function g likewise will be expanded in terms of points x prime and using weights beta. And here these can be arbitrary numbers, etc., just like in the definition down here. Okay, now we have to define a dot product. And not just any dot product, we want a dot product which has this very special property that this thing here will hold true. So in particular, so therefore, if we rewrite it in terms of how we have actually defined this mapping phi, so we're saying phi takes x into the kernel sitting on x. So if we want this to be true, it actually now means that a kernel centered on x and a kernel centered on x prime should have a dot product that's equal to k of x, x prime. So if we manage to do this, then this equation holds true. The question now is, can we do this consistently, and will this actually be a dot product? And actually, it turns out this will only be a dot product if k is positive definite. That's where we'll have to use that k is positive definite. So let's see. So this is so for this particularly simple elements of our space, we want the dot product to take this form. But I also have to tell you how the dot product looks for this kind of elements, because they are also part of our space. And of course, we have no choice how to do it because we want a dot product, so it has to be linear. So therefore, it has to be such that it's actually the linear combination over these coefficients of this. So for particularly simple f and g, if we just have individual kernels, and all this thing here goes, and we are just left with one kernel on the right-hand side. But if f and g are linear combinations, then these coefficients and these points will also appear in the dot product, and it turns out then this is our definition here. And yeah, so maybe I don't dwell on this too long, so that's the definition. And it turns out, maybe that's interesting for the mathematicians among you, it turns out it's easy to prove that this is well defined in the following sense. So when I write functions in this form, it's not clear that this kind of expression is unique. So it might be the case that a function here can be written in multiple different such expansions. It turns out actually this expansion will only be unique if the kernel is strictly positive definite. So in general, we don't know whether it's unique. It might be non-unique. There might be multiple ways of writing the same function. Now the dot product should only depend on the function. It shouldn't depend on how we express the function. So to show that it doesn't depend on how we express this function, we have to use some trick. We can actually rewrite this thing here by looking at it and comparing it to the definitions of f and g. We can rewrite it in two ways. And I'm not going to go through this on the blackboard now, but if you want, you can try this out afterwards. This is it's elementary. We can rewrite it in two ways. And the interesting thing is that this first expression shows us that the value of this dot product does not depend on the betas, and it does not depend on the x primes, right? Because it only depends on beta and x prime through g, and g, of course, it's allowed to depend on g. It's a function of g. And the second expression shows us it doesn't depend on the alphas and on the x's. So it's actually this expression is independent of all these, of the exact way how we have written these functions. It's really just a function of the functions themselves. Okay, so that means it's well defined from a mathematical point of view. It's also easy to see it's symmetric here because it's alpha, beta we can interchange, and the kernel itself is also symmetric, so it we can change f and g, the roles of f and g, and we get the same thing on the right-hand side. And also it's bilinear by a similar kind of argument. Okay, so and I haven't used the positive definiteness yet. Okay, so there's this thing that I've already mentioned before, but I just want to point it out again because it's important. So if we, one special case of our definition of the dot product is this one down here. So it's a special case if we have functions f and g that are trivial that correspond to just one kernel each. In that special case, we get this equation here, which is actually the equation that justifies the term reproducing kernels. So you take a kernel with itself, you get a kernel again. Another special case is if only one of the two functions is trivial. So one of the functions is just a simple kernel, and the other function is a general expansion like this. So in that case, it's also easy to see that the dot product actually reduces to this equation here. So that means if we take a generic function g and take a dot product with a single kernel sitting on x, this kernel actually, in a sense, evaluates g at the point x. So that's in this sense, one also says that the kernel represents the operation of point evaluation. This is also interesting, and it's so this will be a so-called Hilbert space afterwards. But the interesting thing is it's a Hilbert space where all functions, all point values of functions make sense. So in a generic Hilbert space, if you're, I don't know, if you're a physicist and you know quantum mechanics, you usually work these L2 Hilbert spaces where the values of functions at individual points often don't make sense because essentially the elements of these Hilbert spaces are equivalence classes of functions that can differ on individual points. But here actually each value at each point makes sense, which is kind of nice because we also want to make predictions at the individual points. We don't want to make equivalence classes of predictions. Okay. So yes, so now we have everything together. We know it's a dot product. it's well defined and has all the properties of a dot product. Well, almost all the properties of a dot product. What I haven't shown yet is that it's positive definite. Right? A dot product has to be symmetric, bilinear, and positive definite, which means that I have to show, if I take a dot product of a function with itself, the value will be non-negative. And we can prove this using so I'll have to show that it's positive definite and even strictly positive definite. We'll do that in 2 steps. Let's first show it's positive definite. Okay, so that means if I take a dot product of a function with itself, then I get yes, I get a non-negative value. Okay, so what we do is we first show that this quantity here is a positive definite kernel on a set of functions of this form. So maybe that's yes, yeah. And then we can use the properties of positive definite kernels to show actually that it has this property that we need for the dot product. So I hope you don't get confused about kernels on one side, dot products on the other side. Okay, so let's do the following. So we consider this set of functions here, and now we write down this equation, which is what we would require for a positive definite kernel on such functions. So let's look at this quantity here, and let's now first we use bilinearity of this thing. So we already know that this thing is bilinear. By definition, we know it's well defined. It's bilinear, symmetric. So let's use the bilinearity. So we move the sum and the coefficients in here. So then things look like this. Now we notice that this and this is the same. Let's call it f. Okay. Now we know that all our functions can actually be written in this form. So let's express this particular function in this form. And now we move the sums out again. To get this thing here, we are using also the fact that we know the value of this of our bilinear form for a kernel with another kernel, which is actually, again, the kernel is the reproducing property. So we've only used things that we already know. Now this thing we know is non-negative because K is a positive definite kernel. Okay? So that means from the fact that K is a positive definite kernel, it follows that this thing here that we have defined with the angular brackets is also a positive definite kernel, right? From this sequence of equations here, we now know that no matter what gamma I, gamma j we choose, and no matter how many, and no matter which functions we choose here, we always get this inequality. Therefore, this thing that we have defined so far, of which we know it's symmetric bilinear, is actually a positive definite kernel. And in addition, so that's nice. In addition, we can show that it's strictly positive definite, which we also need for a dot product. And strictly positive definite means that a dot product. So positive definite means that VV is non-negative. Strictly positive definite means that whenever VV equals 0, then V is equal to 0. Okay, so we have to show this as well, and then we have all our properties together. So let's do this as follows. So in our case, the V's are functions. So for a function to be 0, we have to show that it's 0 everywhere. How do we do this? Let's look at our function at some arbitrary point x. Okay, we have to show. So I'll show you now how to do it. So we evaluated some arbitrary point x. Let's raise it to the power of 2. So first of all, we rewrite this quantity here as the dot product of the function with the kernel, which, as you remember, is the representative of point evaluation. So to evaluate f at x, we have to take the dot product between f and the kernel centered on x. So let's do that. Now we use the Cauchy-Schwarz inequality. So this quantity here, it's still somewhere written here. Now our positive definite kernel is the thing with angular brackets, but this property still holds true. So we can upper bound this by the dot product, or by the positive definite kernel of the first element with itself, and the same of the second with itself. Which one actually? This is also equal to k of xx, but it doesn't matter for us now. Main thing is now we have this quantity here, which is upper bounded by the product of this and this, which means that whenever our positive definite kernel of f with itself is 0, so if this quantity is 0, then we have an upper bound on this which is 0, and this is a square, it can't be negative. Therefore, whenever the blue thing here is 0, f of x is 0, and this argument is independent of which point x we choose. That means whenever f is 0, the function is identically 0. So therefore, we now have all properties together, and we know that this quantity with angular brackets is a dot product, so we can start calling it a dot product. And then the next step is trivial. So now it's a linear space with a dot product. It's sometimes called a pre-Hilbert space. And then there's just this operation of completing it in the corresponding norm, which you don't have to worry about. And then we got what's called a Hilbert space. So if you don't know Hilbert spaces, don't worry about them. It's essentially just a vector space with a dot product. Okay, so any questions about this? Okay, so then I should soon move to the kernel quiz. Yeah. So I'm going to skip some materials. Just want to mention there's this thing which is sometimes useful. So let's think about this feature map for a second. So this is the thing that we had constructed. Each point is represented by a function sitting on this point, or by the Gaussian sitting on this point, which in a sense means what is a function? A function is just a collection of its values for different inputs. So that means each point is now represented by all similarity values between that point and arbitrary other points. Right? So if the kernel is a similarity measure, our representation in the Hilbert space means each point is represented by all possible similarities to other points. It turns out if we don't have all other points, but just a sample of other points, we can also represent the kernel just by its similarity to a sample of other points, and that can be a reasonably good approximation. So a sample of other points from x1 through xm. So that means we would map into this kind of space. Now remember, in this space we were using a somewhat non-trivial kind of dot product. So the dot product was defined such that this reproducing kernel property holds true. So now if we instead go to this finite dimensional space, we can't expect that we can just use the canonical or the Euclidean dot product in that space, and this will somehow correspond to what we would have done in the function space. But it turns out we can reconstruct essentially an approximation. And it turns out the approximation will look like this. What we should be doing this kind of rescaling. So we don't just map into these points, but we rescale them by the k to the minus 1/2. And then it turns out we get the right kind of values for essentially we get this reproducing kernel property again in this subspace, so in this lower dimensional space. And we can also reconstruct this using kernel PCA if you want. So I'm probably not going to have time to talk about kernel PCA, but it turns out this corresponds to performing kernel PCA and then working in the kernel PCA subspace spanned by these M points. Okay. So let's do... I left a lot of slides in that I knew I'm not going to talk about, but I thought it might be useful anyway for you to have them. So this is an important thing that I briefly want to talk about, the Mercer Theorem. So turns out there's this beautiful property that if we have a kernel algorithm which minimizes a regularized risk, which I think Steve said is a dirty word, so we minimize this quantity, but it's a fairly generic quantity, which looks as follows. So we have a positive definite kernel. We have some training set. When we have a pretty much arbitrary cost function, so let's not look up here, let's look here. The cost function that depends on all the training pairs, xi, yi, and on what our prediction. So now our goal will be to find some function that somehow explains this training set. So in the cost function, we'll have access to all the training points and to the output of our prediction. So for instance, it could just measure the squared error between yi and f of xi. But it could do something more complicated if you want. It could do it in a way that depends on x, or it could even do it in a way that sort of jointly combines everything together. But the crucial thing is the cost function depends on f only at the training points. So if this is the case, so this is like a very general type of cost function, plus we have this quantity here that depends on f globally. That's the regularizer, right? So all this is depending on f locally. This is a global thing, and we assume that this is strictly monotonic. So for instance, it could be the norm of f squared. So this is the norm in the reproducing kernel Hilbert space. I just told you how the dot product looks, so you know how to do the norm. It turns out that any minimizer of this thing here can be written as an expansion in terms of kernel functions centered on the training points. So that's quite surprising, because this is actually, if you want, this is minimizing this thing here over the whole reproducing kernel Hilbert space. So I told you this can be an infinite dimensional space. So this is an optimization problem in an infinite dimensional space. And it turns out that the solution lies in this m-dimensional subspace, and we can find it, for instance, just by optimizing over the alpha i's. So that's why support vector machines can solve a problem in an infinite dimensional space in finite time, because you just have to solve this over these coefficients in front of the training points, essentially. Is a question.
Is it possible to enforce sparsity on the alphas in your function?
Yeah, you could. So you couldn't do it. Well, it would require some thought whether you can put it directly into here, but it turns out that for certain cost functions you get it automatically. For instance, for an SVM in classification or regression, you will get a form of sparsity as a consequence of the geometry of the problem. But if you...
It's still too large.
Yeah.
Is it possible to
Mm-hmm. Yeah, one would have to think about whether one can prove something if one just puts something with alpha I in here, because the thing is, so maybe one would have to think about the strictly positive definite kernel case where there's a unique correspondence between f and alpha I, because if f can be written in different ways in alpha I, that's already a little bit of a mess. But if there's a one-to-one correspondence, yeah, I think we have to talk afterwards. It's not clear, but probably something can be done. Yeah, maybe it would be interesting to think about whether one can prove representative theorems for such settings. It's a pity Massi just left. He might have been able to answer this. You can talk to Massimiliano Pontil. He has worked on sparsity lately. Okay, so 10 minutes. Yeah, I have to hurry up because I want to get to the quiz. Okay, so I'm not going to prove this one. It's very elementary, the proof. Actually, this is a funny story. So this theorem, the original version was due to Kimmeldorf and Warbar. It was actually in the PhD thesis of Warbar, Grace Warbar. She's a statistician in Madison who's now close to 80, but still traveling and doing lots of sports. She was here a few months ago. So she proved this, and people in the kernel community kind of knew that there's this proof, but I think nobody understood it. It looked very complicated, and it's written in a completely different notation. And then at some point, I suddenly noticed actually it's very simple to prove this result, and came up with this very elementary proof, which I recommend you can take a look at because it's very easy. And then also we noticed that this elementary proof also works in a more general case. So this is slightly more general than the original statement. Yeah, and also I should say it has recently been generalized in various directions, and maybe I want to point out two, because this was work done here in Tübingen. One is for a setting where you have some additional linear operators in here. One is for a setting where you're actually essentially you want to work with training points that are not points but probability measures in their own right. So suppose you only know the points up to some noise, so each observation is a little distribution in their own right. And then you can write down modified risk functional where you are now taking expectations with respect to these little distributions. So for instance, think of them as little Gaussians, but they could be Gaussians of different width. You might have different uncertainties for different points. So you have these little Gaussians in here, but you also have a Gaussian kernel. And then you can prove a nice representer theorem which shows that the solution of such a problem is an expansion where over here essentially you get the convolution of these Gaussian kernels. So you get slightly broader kernels where each kernel, so now in this expansion there might be different kernels in the end, different widths, depending on the different training points, and each kernel has some uncertainty that's due to the training point uncertainty, and it has some width that's just due to the choice of the properties in kernel Hilbert space, so the choice of this original kernel. So if you want, you can take a look at that. Okay, I think I cited it somewhere. Where is it? Yeah, this one. Okay, so support vector classification, I think you'll get to know it in the practical course, but if you want, you can say that it's just a special case of what I just showed you with this particular cost function. And I can also make my life easy saying kernel PCA, which I won't have time to talk about in detail, is also a special case with this particular somewhat funny cost function. This is a cost function that sort of combines all points together, and yeah. So kernel PCA. So who knows kernel? Who has heard of kernel PCA? Okay, that's about half. Yeah. So kernel PCA is just principal component analysis carried out in the reproducing kernel Hilbert space and written such that it only depends on kernels, so it requires a little bit of algebra, but then in the end you get something that only depends on kernels, so that can be done efficiently. Okay, and I wanted to, I won't have time for this, but maybe for those of you, so who knows spectral clustering? Okay, for those who are interested in this kind of stuff, I have some link here that is kind of, I think I never put it into a paper somewhere, but it's kind of interesting for those who are into spectral clustering. There are these algorithms for spectral clustering that look quite different from kernel PCA. They work with this so-called Laplacian that's defined in terms of kernel matrix or similarity matrix. And then they take this matrix, do an eigenvalue decomposition, and compute eigenvectors, the leading or the smallest or the second smallest. And then the embedding of the training points will be read off the entries of the eigenvectors. So the length of the eigenvectors will be equal to the size of the training set. And you can read off the embedding coordinates. So these are dimensionality reduction algorithms from the entries of these eigenvectors. And that looks fundamentally different from kernel PCA, because in kernel PCA, you compute these embeddings by mapping a training point into the feature space and then projecting on eigenvectors. And then you get solutions like this. So that looks very different. However, the thing is, in kernel PCA, this is a general embedding for any point x, whereas the spectral clusterings only deal with the training points. So they only give you an embedding for the training points. And if you substitute a training point in here in kernel PCA, then actually this is just a matrix vector dot product. And this is the eigenvector of this matrix. And then we can also simplify that. Then we are also just left with the eigenvector itself. So essentially, we get something very similar in the special case that we project the training point. We also get essentially the entries of the eigenvectors, and there's some discussion in here. If you're interested in this kind of stuff, you can read it afterwards, so we can talk about it some other time. Okay. So the main message, and then I get to the kernel quiz, is the kernel is a similarity measure for the data. It gives you for free a linear representation of the data. We have constructed it. We have constructed the feature space in which our data are vectors. And due to the representer theorem, it also parameterizes the hypothesis space that we use for learning, because we don't know the solutions of a kernel algorithm are just expansions in terms of kernels. So that's nice. And now I come to the quiz. Oh. Okay. Okay, so wait. Okay, so the trick is, so maybe you take a piece of paper and you always write your responses and keep track, and at the end we'll have one winner. You just have to be honest, yeah? Maybe your neighbor can watch you whether you're cheating. So whenever you get it right, you write a plus, otherwise you write a 0 or something like that. Okay, and this is going too fast. I cannot give you reasons for all these things, all these kernels, and if you have questions, ask me afterwards, but I might have forgotten the answer, the proof, so I might have to think about it. Okay, so is this a kernel, yes or no? You have 10 seconds. You have to write a plus or a 0 on your... no, wait, so you have to write yes or no. The plus or 0 comes afterwards when I give you the response. So just write yes or no, and afterwards you grade yourself. Kernel, yes or no? Okay, it's a kernel. Okay. How about this one? Kernel, yes or no? It's not a kernel. How about this one? Is it a kernel? So when I say is it a kernel, I always mean is it a positive definite kernel? Okay, write it down, and it's a kernel. How about this one? So here, it's a kernel in the middle, so we assume this is a kernel, but we multiply it with a real valued function from left and right. Is it a kernel, yes or no? Write it down. It's a kernel. How about this one? This time I multiply with minus a function left and right. Is it, don't tell your neighbors. Is it a kernel? Yes, okay. Next one, the cosine of the angle between two vectors. And this time we assume that these are actually vectors. This is a dot product space actually here. Okay, 3, 2, 1, 0. It's a kernel. Okay, how about this one? So just real numbers, x, x prime, the maximum. Is that a kernel? 3, 2, 1. Oh, not a kernel. How about this one? Minimum. Say again? What's R plus? Oh, R plus, just the non-negative numbers. No, actually, positive numbers. Actually, no, I guess non-negative is also okay. Yeah. Okay, is it a kernel? Yes. Okay. Yeah, non-negative is okay here. How about this one? So here we have K prime, a kernel on some domain X, but we first have a mapping from, sorry, K prime is a kernel on Y, but we first map X to Y in here. Is that a kernel? We have to guess fast. 3, 2, 1. It's a kernel. Next one, delta function on x prime, or the indicator. So whenever x is equal to x prime, it's 1 and 0 otherwise. It's just a test for identity. So don't say it, just write it. 3, 2, whenever you see it starting rotating, you cannot write anymore. Okay, it's a kernel. How about this one? And don't get confused by the fact that I've already called it a kernel. That might be misleading. So this is well, just read. It's the indicator function, or the function. This thing is 1 whenever, sorry. Yeah, well, it's the indicator function on this set here. No detailed discussions. You just have to guess. Is it a kernel or not? Yes. How about this one? Exponential of a kernel. Is the exponential of a kernel a kernel? And if I write something like this, then of course I want it I want it to be a kernel in general. So if there are cases where this is not a kernel, then the answer should be no, right? So I wanted the general statement. It's a kernel. Oh, how about this one? The log of a kernel. Certainly, if I take a kernel and exponentiate it and then take the log afterwards, that's good. But I want to know in general. Yeah? Is it a kernel? No. But it can be, as I just said. Yeah. Okay, so now second page. This is getting a bit stranger, but we're almost done. So how about this one? So here, P is a probability measure, A and B are events or sets. Yeah. Is that a kernel? Yes. Now I'll make it a little bit harder. I subtract something from the diagonal. In a sense, yeah. So is that still a kernel? Yes. So you can show this by constructing a feature mapping if you want. We can discuss later. How about this one? Well, this one should be easy. I've shown you this one already. Is that a kernel? Yes. Okay. Well, how about this one? 3, 2, 1. Not a kernel. How about this one? It's a kernel. Okay, here, this is a slightly stranger one. Maybe I'll give you a few more seconds to think about this one. So here we have H is the entropy of some random variable, discrete random variables. This is the joint entropy. So this is the definition of the mutual information. So the question is mutual information a positive definite kernel? This is non-trivial. This was open until very recently. It's not. How about if we only have up to 3 points? Might that be a kernel? So which means like for 3 by 3 matrices, so 3 random variables. Yes. Okay, and now the last one, and I hope I got that wrong because I only came up with this one at 1 a.m. last night when I finished my slides. Okay, this one I will not tell you now. You have to solve it afterwards, or you think about it over lunch or in the break. I give you 2 things, and one of them is a positive definite kernel. So one is, so we consider integers as inputs, and we consider as definitions either the least common multiple of the 2 integers or the greatest common divisor. And I'll tell you that one of the 2 is a kernel, but you have to work it out yourself. So, so please add up your pluses, and then I have to come up with a price. I think I have something in my office. I'll have to. You'll get it afterwards, but the price is the first book about dedicated to SVMs, which is actually my PhD thesis, which was it was formally published as a book by a very small German publisher, so you won't have seen it anywhere. And maybe it's a collectible, maybe not. But anyway, you'll get. But you should not cheat. So your neighbors are checking. So let's see. Who has? Is there anyone who has more than 10 points? Ooh, okay. How about more than 12? How many questions did I have? More than 15? Wow, okay. More than 50? Okay, you're not allowed to play anymore. No, more than, no, seriously, more than 20? I don't think How many questions?
20.
There were 20 questions. Okay, more than 16? 16 or more? 17 or more? Oh, wow. Okay, you should come and give this lecture here. 18 or more? Okay, so go 17 or more? Oh, okay, there's 4 of them. We have to, okay, then whoever gets the best solution for the greatest common divisor or least common denominator of the 4 of you. So let's say we meet in the afternoon break and you give me your solution of that problem. Ideally, not just the answer, but also a proof. And who gives the best proof gets the prize. Okay, thank you very much.